Thank you, and hello everyone. I'm going to go ahead and get set up. All right, so I want to say good evening and welcome everyone again to our Models to Math Mastery. I am Melody McDuffie, an elementary math specialist with Academic Services. All right, so here's our agenda for this evening. We're going to look at counting as a foundation for addition and subtraction. We're going to look at number lines to solve, place value strategies, tape diagrams, and then we're going to close with some questions. So from this session, we hope that you will learn to, participants will be able to know how to incorporate a variety of math models to solve problems and be able to understand the importance of these math models as students progress through phases of learning. So let's get into it. In mathematics, we focus on the phases of learning, which I've just spoke upon. The phases of learning are the process used to represent students' thinking and learning. So they start with the concrete, which is the doing stage. They use models where they can physically move objects to represent a problem. Then we'll go to representational. This is the seeing stage. Here's where students visualize representations of concrete objects that are used to model problems. And this stage encourages students to make mental connections between the physical objects that they were handling to the abstract pictures diagrams that they're going to be representing. Then we have our abstract. Our abstract is the symbolic stage, where students use abstract symbols to model problems and begin to make sense of various algorithms. Students will not progress through this stage until they've demonstrated a solid understanding of the concrete and representational stage. So let's jump right in. Counting as a foundation. So research on early counting suggests that all children would need help developing the following interrelated aspects of early numerical knowledge. You have number sequencing, which is the names and order of numbers. One-to-one correspondence, which means that as they move or touch an object, they realize that it's a one number for that particular object. Cardinality. So that's the understanding that the last number I said represents that group. And then subdizing, the ability, to recognize a small group of objects without counting. And students are introduced to this when they have the 5 frames and then they go to 10 frames. So being able to see that, oh, that's 5 or that's 10. Addition and subtraction of whole numbers are based on sequential counting of whole numbers. So when they're counting objects arranged in a line is the easiest, of course. With more practice, students learn to count objects in more difficult arrangements, such as a rectangular array we see with the apples. Then we have the circular that we see with the pairs. So they need to be able to stop just before they start, just before counting the same pair that they started with. So making sure not to repeat. And then they go to the scattered. They also learn to count in a specific pattern when they have a scattered objects. So now let's take a look at some of these counting strategies as they apply with our math. So some research has demonstrated that when kindergarten and first grade students are regularly asked to solve problems, not only do they develop a collection of number relationships, but they also learn addition and subtraction based on those relationships. So the student represents this problem with objects. They'll put 2 counters for the 2 apples, and then they'll put 3 counters for the other 3 apples, and then they'll count 1, 2, 3, 4, 5. So they're counting all of them, which is one strategy. Another counting strategy would be counting on from the first number. So based on a problem, Avery has 2 apples. He picks 3 more. How many apples does Avery have? Avery starts with 2, which is, indicated with the circle around the first 2, and then they'll count, they'll count from that 2, 3, 4, 5. So they'll lump those first 2 together and count on 3, 4, 5. Here, they're doing a count-on strategy, but their understanding of small and greater than, less than will help them determine that I can count on from the bigger number, which is 3, and then just add 2. So I have my group of 3, and I'll count 4, 5. So that's their counting on. And with this strategy, the student informally leverages the commutative property, which is the understanding that changing the order of the add-ins does not change the total. So we're going to move on to some of our number lines to solve, excuse me. Number lines are useful methods for developing an understanding of addition and subtraction. Students can use this tool to extend their understanding of counting on and counting back to add and subtract numbers. A number line can be helpful in visualizing the actions of the addition subtraction problem. So here we have a second grade example. We're going to add 58 plus 15. And here I'm going to show you 2 ways that students could use the number line to add these 2 numbers. So first we're going to start with 58. We're going to add 10, but it's easier to add that group of 10 from 58 to 68. Then we're going to add 2 to get us to 70, which is a multiple of 10, and then add 3, which gives us 73. So you see, we decompose that 15 into 110, and then we into 10, 2, and 3. Another example, instead of decomposing 15 into 10, 2, and 3, we can add 2 to 58 to give us a multiple of 10, which is 60, and then we can add 13 to get us to 73, because again, we know that when we add that the 10 place, that 110 to 6, it'll give us 7, and we add those 3 ones. And both of these strategies allow us to add accurately without worrying about regrouping or focusing on that, which could cause some miscalculations. Here is a subtraction example. Again, a second grade level subtraction. So with subtraction, we're going to start with our whole number, our total, or what we have, and we're going to go backwards because, again, we're subtracting. So here, I'm going to decompose that 233 into 200. So 472 minus 200 gives me that 272. Then I'm going to subtract 30. I get 242. And then I'll just make little jumps to subtract ones till I get to 3 ones, and that's where I end with 239. So 472 minus 233 will give us 239. Again, number lines are very useful because as you can see here, we're going to use it to solve a multiplication problem. So the result of multiplication is the total number or our product that would be obtained by combining several groups of the same size, which is repeated addition. So we're going to start at 0, and we're going to add groups of 9. So each time we jump or we demonstrate or represent that jump, we're going to add 9. So we go from 0 to 9. That's one group. Add another 9 gives us 18. Another 9 gives us 27. And our last 9 gives us 36. So as you can see, we added 4 groups of 9. So 4 groups of 9. There are 4 jumps, and each jump, represents 9. And we can do the same with division. So using the number line, division is the action of separating something into parts or fair sharing. So this means the result of division can be obtained by repeated subtraction. So we would start again at that end and work our way backwards because we're doing subtraction or repeated subtraction in this case. So starting with 27, I'm going to repeatedly subtract groups of 9. And I'm going to keep subtracting groups of 9 until I end with 0. And the number of jumps indicated tells me that 27 divided by 9 equals 3. That was a third grade example. And you can see the example grade levels below where it has a below at the either at the bottom, or at the top, but it'll indicate what grade level this is appropriate for. Here's a fourth grade example. Now the fourth grade example is going to be a little different because we're going to do a little bit more decomposing. So we have 42 times 7. We're going to decompose or break that 42 down into 40 and 2. So we have 40 times 7 plus 2 times 7. Starting with our number line, starting at 0 because we're multiplying, so we're increasing. We're going to start with 40 times 7. That gives us 280. Again, a multiple of 10 makes it easier to work with. Then we're going to multiply 1 times 7, and then 1 times 7 again for us to end at 294. So 42 times 7 equals 294. Now, you could also do one jump where you're multiplying 2 times 7 to get that 14, but it matches the decomposition that we have here, which is why I did it 1 times 7, 1 times 7. Here's a fourth grade example with fractions. Again, starting at 0, that first number tells us how many groups we're going to have of that number. So 5 groups of 3/4. So we're going to have one group of 3/4. We'll do another 3/4, and we'll have groups, which gives us 15/4. Again, this is with a multiplication of whole number times a fraction. All right, so we've covered some number lines. I want to take a look at some place value strategies. These are where some students will be able to demonstrate their understanding of place value. So first, we're going to start with some place value disk. And the disk we're going to use, we'll have our place value table. We're going to represent the first number 47 here. So 47 is made up of 4 10s and 7 1s. We're going to add 2 1s. And as we add, we're going to start in our ones place. So our ones place, we have 9 1s, excuse me. And our 10s, we have 4 10s plus 0 10s, which gives us 4 10s. So 47 plus 2 equals 49. So again, here, I just want to explain really quickly that these are place value disks. The place value disk, they're different from the chip model, which we will see. The place value disk, the numbers represented on them represent 10 times the previous amount. So you can see here the greens are 1s, and then my 10s are 10 times that 1. And if I had hundreds, it would be 10 times my 10s. So that's how you know you have place value disk. Another example, this is second grade with place value disk. This is a subtraction, so it's going to look a little different. I'm going to start with my 62. So that's 6 10s, 2 1s, and I'm going to subtract 47. I'm going to subtract, since I'm going to subtract 47, I'm not going to represent that 47. I'm going to actually start subtracting that amount from what I see. So I have 62, 6 10s, 2 1s, and then I have 4 10s, 7 1s. I'm looking and I notice that I do not have enough 1s in order to subtract I only have 2 1s and I need to subtract 7. So in order to do that, I need to decompose one of my 10s into 1s. So to represent that, I'm going to cross out a 10 and break it down into 1s. Now I have enough to where I can subtract. I'm going to subtract my 7 1s. And I'm going to subtract my 4 10s. Looking at what's left over, I see that I have 5 1s and I have 1 10. So 62 minus 47 gives me 15. So again, place value disks are what we just used. The next model we will focus on is the chip model. The chip model is a more representational model where students use one color of chips to represent the numbers. This helps students to make a connection to the written method, a standard algorithm, To use a model with addition, we're going to begin with an empty place value chart. I'm going to represent that first number, 215. And then I'll represent my second number, 158. So as I start to add, beginning in my ones, I realize that my ones place has 13 chips or 13 ones represented here. With my understanding of place value, I know that I cannot have two digits in one place, which means I need to bundle or regroup or rename these 10 ones here as a 10. So once I do that, it's no longer there, it's represented in my tens. And with the standard, with the written method, you can see it indicated here where that blue one at the top represents that 110 that we regrouped, and the 3 blue represents our 3 ones that's remaining. So I count my tens, I have 7 tens, and then I add my hundreds, I have 3 hundreds, which leads me to understand that 215 plus 158 gives me 373. So again with the chip model. Second grade example. Here's another second grade example with place value disc. So I'm subtracting 326 minus 182. So like I stated before, because I'm subtracting, I'm not going to represent that second amount. That second amount will be taken from what I have, that 326. So starting in my ones, I know I need to subtract 2 ones from the 6 ones that I have. I have enough. I'm going to go ahead and do that. Once I do that, I have 4 ones. Now I'm going to my tens. I see that I have 2 tens and I need to subtract 8. So again, with that place value understanding, I know that I can go to my hundreds place, regroup one of these hundreds as 10 tens because 10 tens equals 100, and then I can subtract. So that those 10 tens that I decomposed from the 100 plus the 2 tens I had gave me 12 tens. I subtract 8 tens from those 12 tens. I have 4 tens, and now can I'm looking at my model, excuse me. I see that I have 2 hundreds when I originally started with 3. I need to make sure I indicated that I decomposed one of these hundreds from that 3. And that's where I would cross out the 3 and put a 2 because again, I decomposed 100 here. Now that I have 2 hundreds, I can subtract 100, which leaves me with 100. And 326 minus 182 will give me 144. Using place value disc for third grade example to show multiplication. Still starting with that place value chart. I have 3 times 6, pretty straightforward. So to represent my 3 times 6, this first number represents my number of groups I'm going to have, and the second number represents the amount in each group. So here I have 3 groups, which I'll indicate with these lines. The top group, the first one is one group, the second is the next group, and then the third is the third group. Then I'm going to add 6 ones to each group. And since I said 6 ones, I'm going to make sure I line it up and put it in my ones place because we have to do something with that. So I have 6 ones here, 6 ones here, and 6 ones here. I can see or I can count that all of these total 18. But again, I know because I understand place value, I know I cannot have these 2 digits in one place. So I'm going to bundle one group of 10 and regroup it to my tens place. So now I have 8 ones that are no longer bundled, and then I have 110. So 3 times 6 equals 18. That was our multiplication. Here's our division example. Like I said before, that division is is basically our repeated subtraction or fair sharing. So that's what I'm going to use in order to demonstrate this with our place value disk. I have my place value chart. I have a total of 20, excuse me, 20 uh, place value disk. I have 20 of whatever it is, which is represented here with my two tens. I'm going to fair share, equally share these 20 into four groups. And these lines represent my four groups. Looking at my two tens, I know that I cannot fairly share those unless I decompose or break those tens down. So I'm going to break or decompose this 110 into 10 ones. And I'm going to do the same with this 10 and decompose that into 10 ones. So I have my 20 ones here, and I'm going to go through and equally share. So each one gets one until all of my ones, or until all of what I have is gone. I have no more tens. So in order to determine what 20 divided by 4 is with our model, I can count this first group or any group because I know that each group represents the quotient. So the amount for each group is represented by the quotient. So 20 divided by 5 equals 4. I'm sorry, 20 divided by 4 equals 5. So again, the size of my group is my quotient. All right, so a fourth grade example here where we're dividing one digit by 3 digit. Start with place value chart. I'm going to, represent my number 702. And again, with division, I'm equally sharing. So I'm going to go ahead and set up my groups, my 3 groups, and I'm going to start sharing. I'm going to start with my hundreds because I see I have a good amount of hundreds. So I'm just going to start sharing my hundreds. Once I do that, I realize I have 100 left. So I can't share that 100 evenly or equally, unless I decompose it. So once I decompose it, I'm going to break down that 100 into tens. Now give me 10 tens, and then I'm going to start equally sharing again, same process. And again, I end up with a 10 left over. And again, I will decompose. So I'm going to keep breaking it down until I can evenly share everything. And then with my ones. I was able to utilize all of my ones equally within the groups. So 702 divided by 3, again, the size of each group is my quotient. So if I look at the size of one group, which is 200, 200s, 3 tens, 4 ones, 234, I know that 702, divided by 3 is going to give me 234. Fifth grade example. Now we're going to demonstrate division of decimals using the chip model. So again, we're going to the chip model where one color is used to represent the number, but we're still going to do the same process. Okay. So when working with decimals, if you just look really quickly, you can see that my place value chart looks different. I have ones, decimal, tenths, hundreds. Before I was to the left of the decimal place, so I didn't need the decimal place to represent because I was working with whole numbers. Now I have 4 and 2/10 that I'm going to equally share. So 4 and 2/10 divided by 3. I'm going to start with my represent my 4 wholes, so my 4 ones and 2/10. I'm going to make my equal groups, my 3 groups, and I'm going to start equally sharing. So starting with my ones, I've used my 3 ones. I have 1 left. We're going to do the same process. We're going to decompose that 1 into tenths, which gives us 10 tenths plus 2/10, which is 12 tenths we are going to equally share. So I've equally shared all of my tenths. I can look at one group size. Again, that one group size is going to tell me my quotient for this division equation. So 4 and 2 tenths divided by 3 equals 1 and 4 tenths. I just want to reiterate, or I just want to let you all know that that decimal represents the and. So when we're saying 4 and 2 tenths, the students know or recognize that that's a decimal. So if you're saying the whole number, you don't want to indicate or say and in it. You want to make sure you keep it together because it represents that whole. And when you say and or you put and in a number, it starts to represent something different. All right, so our fourth model we're going to discuss or go through are tape diagrams. A tape diagram is a drawing that looks like a segment of tape and is used to illustrate number relationships. So tape diagrams are visuals that represent the section of a ratio by using rectangles. These models can help break down complex mathematical word problems and help to simplify for students to solve. They're depicted in the form of a strip. Sometimes they call them bar model, length model, strip model, or fraction strip. Okay. And some of the benefits of these tape diagrams are it's a thinking tool that allows students to visually represent the problem. It helps students to transform word problems into an appropriate numerical operation. It helps students make sense in reasoning. So our first example here says Madison's necklace has 55 pearls. If 17 pearls fell off Madison's necklace, how many beads are still on? That should be pearls. So how many pearls are still on? So we're trying to figure out the amount of pearls that are still on Madison's necklace. So with the tape diagram, we're going to start that tape diagram, a little bar, that represents our whole. So we know she has 55 marbles, okay? We're going to segment or break off a part to represent these 17 beads fell off. So this little square here represents the 17 that fell off. We're trying to figure out the amount of beads that are still on. So now that we have this set up, we can see that 55 minus 17 is going to give us what is still on the necklace. You can actually also think of this as 17 plus something will give us 55. As we work through it, we'll figure out that 38 beads are still on Madison's necklace. Another example, here is a comparison problem where we're doing compare bigger unknown. This is one of a more difficult problems because when reading it, and I read it, it says Justin and Keith both collect comic books. Justin has 31 fewer comics than Keith. Justin has 61 comic books in his collection. How many comic books does Keith has? So when reading it and students see that word fewer, they tend to just want to get those two numbers and subtract when that's not what the problem is asking. So this type of problem highlights the importance of us drawing out to represent and not utilizing those keywords because I know what I was taught, I would look for those keywords and I would do the same thing that students tend to do with this problem because they see fewer, they automatically think that they're going to subtract and they're not really interpreting the problem. They're not breaking it down. So when we solve this, we're going to have two tape diagrams because there are two people, Justin and Keith. So the first one represents Justin's 61 comic books. The second one represents Keith's amount. We don't know how much he had, but we know he had more than Justin. And that 31 represents how much more he had than, or Justin had 31 fewer. So that difference would be the 31 from Keith's comic book collection to Justin's comic book collection. So in order to solve this, they would actually have to add 61 plus 31 to get Keith's total, which is 92 comic books. Sorry, 92 comic books. So again, that fewer could throw students off. But if they work out and break down the problem so they can have a visual representation of it, they'll have a better understanding and they can solve it correctly. Here is a third grade problem. There are 6 students in the third grade book club. Oh, sorry. If each student reads 4 books, how many total books will the students read? Third grade problem, starting with our tape diagram, our whole we're trying to figure out, we don't know. But with our tape diagram, we're going to partition our tape diagram into 6 parts or pieces because we know there are 6 students and each square will represent 1 student. So I have my 6 squares for each student, and I know that each student read 4 books. So I'm going to put 4 for each of these students, and then I can count and determine that 24 books will be the total that's read. So 6 times 4 is 24. Another third grade example using the tape diagram, but this one focuses on division. Thomas has 28 apples he wants to place into 4 baskets. He wants to place the same amount of apples in each basket. How many apples will be in each basket? So again, my tape diagram represents my whole. I know my whole or my total is 28 because it told me that Thomas has 28 apples. I know he wants to equally share these into 4 baskets. So I'm going to break this tape diagram, partition it into fourths to represent my 4 baskets. So each square is a basket. And then I'm going to equally share. I'm going to equally share apples until I get to 28. So I would count 1, 2. And to determine how many apples are in each basket, I would just need to count one group. I'm sorry. So 28 divided by 4 gives me 7 because one basket has 7 apples in it. And again, that's represented here in our tape diagram. A 4th grade example for those of you who have 4th graders. Sammy is baking cookies. Each batch of cookies requires 2/3 cup of sugar. How much sugar will Sammy need to make 4 batches of cookies? My tape diagram, I already have it partitioned into 4 because he's making 4 batches. And that's what I'm trying to figure out, what that total represents. So each batch is 2/3 sugar. If I add those, I get 8/3. So we have our 4 groups of 2/3, which again equals 8/3 because we did the fraction that had this, that equals 8/3. When we add fractions that have the same denominator, the denominator doesn't change. Adding the number of letters together will give you 8. So 4 times 2/3 equals 8/3. Or you can represent it here as 4 times 2/3 equals 8/3. All right. Here's a really good one for 5th grade. So LaShawn purchased snacks for lunch. She spent half of her money on cookies, 1/4 of her money pencils. What fraction of her money is left? Now, the good thing about this tape diagram is going to help us to make sense of all this information within this problem. So, starting with our whole tape diagram, because as you can see, each amount she spent was a fraction of her total or a fraction of her whole. So we're going to use this tape diagram to represent that. So first, she spent half of her money on cookies. This is all of her money again. We're going to partition that in half to represent half of her money that was spent. So that purple line is half of her money that was spent on cookies. 1/4 of her money was spent on chips. So still looking at the whole, all of her money, we're going to partition the same tape diagram into fourths now because this 1/4 is represented here of the chips. So I'm going to partition this entire, tape diagram into fourths. You can see that with the green. It will overlap in the middle here. So now that I have my fourths, I'm going to represent the fourth that was used on chips, which would be this section here. I cannot use any section over here because it's already been utilized for her cookies. So I would need this 1/4 represented here is going to be the representative of the amount of money used for her chips. Then I have 1/8. So I'm going to take this same tape diagram and I'm going to partition it into eighths, represented with the blue. So looking at what's left here, I'm going to taper off this portion for the amount of her 1/8 of her money spent on pretzels. Now I can actually see how much money or what fraction of her money she has left. But here we're going to go over with our equation what we did. We started with the whole. We subtracted 4/8, which is equal to a half, because again, we're looking at it in the eighths because that was the last partition we did of eighths with the fraction. I took 2/8 here, represented by this 1/4. Then I took another eighth, and I see that there's 1/8 of her money left. All right, I'm going to do one more with decimals for 5th grade. So Charlie has 8 pieces of rope. Each rope is 3/10 inches long. What is the total length of the pieces of rope? Again, here's my tape diagram. My total amount. I'm sorry, not my total. Yes, my total. This strip represents the 8 pieces of rope. As you can see, they're already partitioned into eighths. So each one is one rope. Based on the information, I know that each rope is 3/10 inches long. So I'm going to indicate that by putting 3/10 into each box. Now I'm trying to figure out the total or the whole amount. So what I can do is I can actually skip count by threes. 3, 6, 9, 12, 15, 18, 21, 24 tenths. And that's important. So this will be 24 tenths. I can write 24 tenths, but with my place value understanding, there's no way I can write that as a decimal, because if I were to write it as a decimal, it would actually read 24 hundredths, and that's different. So again, with my place value understanding, I know that I can't have 2 digits in one place. So those 24 tenths, 2 of those 20 of those tenths is going to be regrouped to ones. So I will write it as 2 and 4 tenths. So with all that we went through, why should we use those math models? The tape diagram, the number lines, the place value strategies. Well, they allow students to visualize and represent mathematical concepts. They help students to make connections from the conceptual to the abstract part of learning, and that goes back to that those phases of learning we talked about at the beginning, when they went from the concrete to the representational to the abstract. That helps with that process. These models help with that process. And it actually supports consistency of concepts across grade level, which means they can utilize these strategies as they progress through the various grade levels. So, helping at home, what can you do? Before answering this, I want you to have I want us to all have a consistent understanding of fluency, because that automaticity can be embedded in the ways that you can help at home. So really quickly, fluency these are some things we used to think of fluency, and that was actually indicated or shared with us before. So it focused on speed. It's a skill that utilized for a time test, memorizing facts and procedures, practicing flashcards over and over. Again, these are some things we used to do when we learned about fluency when, before, or years and years ago. But now we have a better understanding of fluency. It focuses on efficient and effective methods of computing. It's easily recalled from long-term memory. It's conceptual understanding and flexible thinking. And it's working on meaningful number activities. So I want to give you an example to help you better understand what this means. We can think of fluency with automaticity. So if you give a child, or if they see the fact, the expression 7 plus 5, we want students to shift from a short-term understanding or short-term memory to putting that information in their long-term memory. And in order to do that, they need to make it connect to something. So instead of saying just 7 plus 5 is 12, we want students to be able to decompose it into either decompose that 7 into a 2 and a 5, to where they can say, oh, 5 plus 5 is 10, add 2 gives me 12. Or they can decompose the 5 into 3 and 2 and make a 10. So 7 plus 3 equals 10, plus 2 equals 5. So again, shifting from that temporary memorization, something I need to know for now, to facts that can be recalled from long-term memory. We want it to store in that long-term memory. And we can help students, and we can encourage students to do this and work with and explore as they work with and explore numbers. So what can you do at home? I can allow students to utilize iReady and Freckle at home, but when they're working, please have them use some paper and pencil so they can solve and work out the problems. That'll actually help them with that automaticity if they can demonstrate the connections that they're making in order to solve the problem. Point out and discuss everyday math with experiences like shopping, cooking, scheduling, sharing with siblings. Have students share their thinking with someone. Allow students to experience a productive struggle. I know it's hard as a parent or a guardian to watch your child struggle through, but a lot of times that productive struggle is going to get them to understand it, and it will help them to remember it. And the last one is a big one, having a positive attitude towards math. I know our experiences with math are different, but we don't want to put our negative connotation on anything and pass it down to the kids. We want them to have a positive attitude about it so they can tackle it and it won't be something that's a chore for them. We don't want them to always get upset when it's time for math. So I would like to thank you all for participating in the Models to Math Mastery session. I'm going to share my contact information with you all, as well as some other specialists. You see my supervisor and the K2 math director. And if there are any questions, I will take questions at this time as I conclude.
Ms. McDuffie, I believe there is one on the chat. It says, is freckle the same as achieve?
No, freckle is not the same. Oh, it was answered. Freckle is different from achieve, but it can be utilized for grades 2 through 5 in math. Achieve is only for ELA.
It was a pleasure having everyone tonight, and thank you so much, Ms. McDuffie.